Now that we've had a chance to take a look at a couple of examples of using either Ka or Kb to solve some problems related to pH with weak acids and weak bases, I wanted to talk a little bit about how the two interrelate. And this will help to answer a question that you might be noticing, which is when you looked through your textbook to find that table of pKa values for common acids, there wasn't a table of pKb values. Now, we still could well care about weak bases, and in fact we're going to see many examples of times that we do. So how do these react? How do they interact? And in what ways can we use the relationship to get better information from that pKa table? Well, to do that, I want to start by looking at a sort of arbitrary example reaction. That is, imagine thinking about some acid HA that's going to react with water, behaving as a weak acid. Okay, great. We've seen this a million times before. We can write out a Ka expression for this. Again, lovely. Okay, that's the acid side. Let's think about the base side for a moment. Well, when we're dealing with a base, that's going to mean a chemical reaction that looks a bit like that, and a corresponding equilibrium expression that looks like that. So, okay, what are we looking at here? Well, one of the things I want you to think about is we're seeing quite a few things show up in both of these expressions. HA is showing up in both. A minus is showing up in both. So what happens if we multiply them together? Doing that, we're literally just going to pull these down Remember, something that shows up on the top and the bottom of a fraction can be canceled. So take a moment, look at this new combined expression, and tell me what can be canceled. So our HA appears in both places, so it's out. So does A minus. So that means that Ka times Kb is equal to the concentration of H plus times the concentration of OH minus. That looks like something we've seen before. That's the autoionization expression. So that means that this equals Kw. That's really, really interesting, because that means that Ka times Kb equals Kw. We know Kw. We can look up pKa values in, for instance, a table. And in fact, if you go to a variety of reference books and look up the behavior of an acid, you're going to very frequently find that they give you a pKa as a handy number that you can walk around with in your pocket as a way to just generally understand how an acid is going to behave. So having that, we can then, in a fairly easy way, find Kb. So Ka and Kb interrelate, and in our next example, our next segment, we're going to look at what happens when we bring together a weak acid and a weak base. Before we do that, I want to take just a minute to cap off this section on acids and bases by making a couple of observations. 1. Equilibrium constants are temperature dependent. Equilibrium itself depends on temperature. Shifting the temperature can shift the value of the equilibrium constant. That was maybe apparent when we looked at something like that cobalt example with Le Chatelier's principle, but it means some rather interesting things for water. 1, it means that the pKb values that you, or pKa values that you look up and use, are going to be useful around room temperature or maybe body temperature, but they're not going to be as useful if you want to go to very extreme temperatures far away from standard conditions. That also means that this dissociation, this autoionization in water, is temperature dependent. And that means something that's kind of wild. The neutral pH in water depends on the temperature. As the temperature goes up, the neutral pH in water goes down. That's a little bit weird. Later on, at the very end of this chapter, we're going to be looking at an expression that allows us to bring together both these equilibrium constant expressions that are such a useful tool for understanding changes in concentration. We'll bring that together with also an ability to vary temperature at the same time. For the moment, though, you'll notice that in virtually all of these problems we're doing, we're going to be assuming that the temperature is constant and pretty close to standard conditions. Last but not least, why do we care? Why is all this weak acid, weak base stuff even worth discussing? Well, you may just intrinsically find weak acids or weak bases interesting, but one of the most important reasons that we care about them is that many biologically relevant molecules, things like proteins, have portions of their structure that behave as either weak acids or weak bases. So to understand the behavior of all sorts of compounds, including ones that are really critical for life, we have to understand the behavior of weak acids and weak bases.